Okay, now we're going to investigate three charges arranged in an equilateral triangle. And we'll make the two bottom charges positive, the top charge negative. We could choose any arrangement we want, but I'll pick this one. And since it's an equilateral triangle, the distance between all the charges is the same. We'll call that distance S. For the side of the triangle, a distance S. So it's the same for all of them. I won't draw all that in. We'll label going counterclockwise Q1, Q2, and Q3. So it's a good idea to label these charges. In this case, we'll let them, as we have done in the past, we could let them be unequal, but just to keep it relatively simple, we'll let them all be equal, and we'll just call whatever they are, 15 microcoulombs, 20 microcoulombs. We'll let them all be equal to the same amount, whatever it is, and we'll call it Q. Now notice, if we focus on any charge, say we focus on Q1, there's going to be two forces acting on it, just like we saw in the previous example, only now it won't be in a straight line. And so we have to worry about vectors and their components. So this is an application of the so-called superposition principle. 2 acts on 1 in an attractive direction. That would be F2 on 1. And it's going to have an I and a J component because it's partly in the negative X direction and partly in the negative Y direction. Since we're in an equilateral triangle and the charges are equal, the force of 3 on 1 is going to be the same magnitude, so I'll try to draw it the same length, but it will be pointing. Attractive force, it's not really the same length, is it? Attractive force on charge going toward charge 3, and that label would be F vector of 3 on 1. Okay, now we need to add these. If I were to write this out, I would write down the sum of the forces on charge 1. It's going to look the same as the last one. It's going to be the vector F2 on 1 plus the vector 3 on 1, but these are vectors, so we're adding components, I and JK components, so in this case we have to separate the I and the J components and add those components. If you need help with this, you should come and see me. This is all vector addition from last semester using the IJK component method. Now let's look at the symmetry. Okay, so this problem becomes easy because the charges are equal and the distances are equal, and it's an equilateral triangle. So you can see that the two x components, I'll draw it as dotted lines. I don't have enough room to label it, but this would be F21x, and the one on the right would be F31x. They're going to cancel. Whereas the y components, they're components, so I draw them as dotted lines. These both go down. My drawing isn't great on this. But those F21y, F31y, they're going to be equal and in the same direction. And so this problem, because of the symmetry, becomes simple. The net force on charge 1, and I'll save the details. If you need help, come and see me, is going to be 2 times either y component, since they're equal. And the y component right? The vector itself, say F21, would be K, Q1, Q2. In this case, because they're equal, that's Q squared. And the distance is the side of the triangle, so that's S squared. That part, in brackets, is the magnitude of F2 on 1. The 2 is because we have two y components, but to get the y component, we have to take the cosine or the sine of some angle. And since I'm not going to go through this right now, you'll work it out. That angle is 30 degrees if we use the cosine. If we use the sine, it would be 60 degrees. So cosine 30 is, I could write it as cosine 30, but I'm just going to put it in the square root of 3 over 2 since I know what cosine 30 is. And you might remember these or ask me if you need to. Sines and cosines of 30, 60, and 45 degrees, we should know those. So square root of 3 over 2. You notice the two 2's cancel. And we know from the diagram that this is in the negative j hat direction. We could put the negative out front. And if I rewrote all this, it would be root 3k q squared over s squared negative j hat. That's the answer.